Hello, and welcome back to the Mechanochemistry discussions. This seminar series is hosted by the NSF Center for Mechanical Control of Chemistry, or the CMCC. I'm Ashley Martini. The goal of this seminar series is to bring the community together. Our seminars stream live on the third Thursday of every month at 10 a.m. Central. They are available to watch anytime on our YouTube channel. If you've missed any of our seminar speakers, I encourage you to check them out. Again, these are all available on the YouTube channel. Also, looking forward, we hope that you will join us for our upcoming speakers. We have a great group upcoming for the remainder of this year. Before we get started, a great big thanks to Dr. James Batiste, the Center Director, Jennifer Belsick, the Center's Administrative Coordinator, and two CMCC students who help and assist with the seminar series. Thank you so much for joining us ahead of time. We hope that you will subscribe to the YouTube channel and watch all of the presentations, and also follow us on Twitter. Quick guidelines before we get started. This seminar is being recorded. If you have any questions and are watching live, please do email them to us at cmccdiscussions@gmail.com, or you can post them directly in YouTube, and either way they will be propagated to the speaker. Finally, I'm pleased to introduce today's speaker. Professor Hajime Ito obtained his master's and PhD degrees in the Department of Synthetic Chemistry at Kyoto University in Japan. He became an assistant professor at the University of Tsukuba and then at the Institute for Molecular Science. He spent 2 years as a research associate at the Scripps Research Institute before joining Hokkaido University. He's now a professor at the Institute for Chemical Reaction Design and Discovery at Hokkaido University in Japan. Professor Ito's research interests include boron and silicon chemistry, luminescent materials, and mechanochemical synthesis. His achievements have been recognized by many awards, including the President's Research Award of Hokkaido University, the Chemical Society of Japan Award for Creative Work, and the Fujifilm Award from the Society of Synthetic Organic Chemistry. Please join me in welcoming Professor Ito.
Okay, hi, hello everyone. I am Hajime Ito, Hokkaido University, Japan. I'm very happy to have a very super opportunity to make a presentation this time for some CMCC mechanochemistry discussions. So mechanochemical synthesis and organic synthetic methods that has received as a lot of attention in the last few years, and there have been many pioneers in this research. As a first slide, I'd like to show you some books and early reviews to pay tribute to these pioneers. When we started our research in mechanochemical synthesis in 2018, we learned a lot from these pioneering studies. So when we started the study on mechanochemical synthesis, we were particularly interested in reactions of organic solids. Organic solids, even if they are reactive with each other, do not mix well in the usual way, and therefore do not react very well. Therefore, in usual organic synthesis, a large amount of organic solvent is added to dissolve the solids and allow the molecules to react freely. In this case, the high cost of the solvent, high flammability, and the environmental impact are significant drawbacks. Also, although organic chemists are not aware of it, the decrease in reaction rate due to low concentration should be a very big problem. In the ball milling reactions, however, by adding a small amount of solvent and mixing vigorously, the reaction can proceed without dissolving the reagents. Here, the use of expensive organic solvents can be avoided, and high concentration enables the reaction with high rates. And the operational simplicity is also advantageous compared to the conventional organic synthetic methods. With this in my mind, we decided to start our research with narrowing down the target reactions. A limited number of reactions are particularly important in drug discovery, Among them, cross-coupling reactions like Suzuki-Miyaura cross-coupling reaction or Buchwald-Hartwig CN cross-coupling reactions are most important, accounting for more than 30% of the total number of reactions. We turned our attention to such reactions at the first stage of our some research. Our first goal was to set up a solid-state Buchwald-Hartwig CN cross-coupling reactions. This reaction is widely used for the synthesis of not only pharmaceutical compounds, but also organic materials such as OLED luminophores. Before or during our studies, 2 examples for CN cross-coupling reaction with ball mill conditions are reported, but almost all examples are including liquid substrates. Because we are more interested in solid-state reactions, we thus began to investigate the reactivity of the solid-state cross-coupling reaction. At first, we confirmed the reactivity difference between liquid and solid substrates under ball mill reaction conditions. In the case of liquid substrates, the CN cross-coupling reaction proceeded smoothly even under the ball mill reaction conditions. However, solid-state substrates did not react well under the same conditions. The reaction was stopped before the full conversion. This suggests that we need to find a better catalyst suitable for solid phase reactions. We first screened an additive that can promote the reaction. We started our study with my very super colleague with Dr. Koji Kubota. So he quickly found that the addition of a small amount of 1,5-COD can drastically accelerate the reaction. In the presence of alkenes, like 1,5-COD, catalyst deactivation was suppressed and the reaction proceeded very smoothly. This alkane additive can stabilize the catalyst. I will show you the details about this stabilization effect later. This catalytic system has been shown to be effective on many substrates as shown here. So I would like to show you other successful examples of solid cross-coupling on this slide. So one of the key advantages of this ball mill process is the ease of scaling up by just resizing the ball mill. The gram scale reaction can be performed without any problem. We also studied Suzuki cross-coupling reaction of solid materials. The Suzuki coupling of mechanochemistry was first reported by Peters and Axelson in 2000. Several groups then reported the Suzuki cross-coupling reaction under the ball milling reaction conditions. But in my opinion, the research for solid materials was still room for improvement in the reactivity. So with the results of CN cross-coupling in my mind, we then investigated the solid-state Suzuki coupling and we applied the 1,5-COD additive, which were effective for CN cross-coupling, and found that this additive is also very effective for Suzuki cross-coupling reactions. So this slide shows you that the ball mill Suzuki cross-coupling reaction can be performed faster with smaller equipment than traditional methods. Such small vials are sufficient for solid-state reactions, but traditional process requires large glasswares with gas lines, reflux condensers, stirrers, oil baths, and others. The mechanochemical reaction is even faster, and the yield of the product is higher than that in the conventional method. As you can see, it is very clear. Mechanochemical reaction is much better method compared to the conventional solution phase method. As shown here, many cross-coupling products are synthesized by this process. With regard to scaling up of the Suzuki cross-coupling reactions, the 100-gram scale reaction was confirmed to be successful with less than 1 mole% catalyst already. This suggests that this reaction is particularly very useful for maybe some industrial use. Next, this slide shows you how additives works to improve the catalytic activity. After the ball mill reactions in the absence of 1,5-COD, significant aggregation of the palladium metal was observed in the TEM image of the crude materials. In the solid-state NMR, a signal of some free phosphine ligand was also observed. This suggests that decomposition of the palladium complex during the ball mill reaction. On the other hand, in the presence of 1,5-COD, the aggregation of the palladium metal was suppressed greatly. Solid-state NMR shows the signal of the monomeric palladium phosphine intermediate. We suppose that the role of 1,5-COD is a stabilizer of the palladium active species under the ball milling conditions. As already shown, the reactivity of the liquid and solid substrates are greatly different under the ball milling conditions. Liquid substrates are more reactive than solid substrates. This phenomenon is not observed in solution reaction systems, but only in the solid reaction systems. We wanted to take advantage of this property to develop a special selectivity that only found in the solid state reactions. So we used the conditions to test this concept. In solution, the cross-coupling reactions proceeded excessively for the 1,2-dibromobenzene substrate, resulting in the major formation of the undesired bis coupling product. However, in the ball milling conditions, in the ball milling reactions, mono cross-coupling reaction products were selectively obtained in ratio of 9:1 because this mono cross-coupling product is solid product. So the reactivity of this solid product is much less than the starting material. This is a liquid substrate. This type of selectivity was difficult to perform in solution, but in solid reactions, it is achieved by taking advantage of the difference in the reactivities between these solid materials and these liquid materials. We tested this selective coupling in various other substrates and found many bis-bromo aromatics were converted to mono cross-coupling product with high selectivity. Selective cross-coupling reaction was used to synthesize compounds with two different aromatics from dibromo aromatics like this one. This can be conducted in one-pot reaction conditions with good yields. We also synthesize a drug candidate very easily through this reaction process. I believe that this method is very useful for the synthesis of such kind of unsymmetrically substituted aromatic compounds. So I would like to share our most recent results for the cross-coupling of very insoluble materials. The solubility problem is one of the most serious issues in organic synthesis. Conventional organic synthesis relies on the solution reaction, but when you need to react insoluble materials, you find a big problem in the reactivity of the materials. One solution we can take is the long reaction time of slurry at high temperature. However, this situ making reaction often resulted in low yield of the desired products. Because the ball mill reaction does not rely on the solvent, we anticipated that the mechanochemical method might solve this long-standing problem in organic synthesis. So we first tested the compound in the ball mill reactions. We tested this compounds in the ball milling reaction, which has very low solubility comparable to the carbon-60 at room temperature. But however, we could not find any progress in these reactions. So next, we decided to do ball mill reaction at higher temperature. There are several methods for high temperature ball mill, but we found that the use of temperature adjustable heat gun is very convenient for this use. This is a very cheap and easy way, and you just do with your ball milling machine. The temperature is can be adjusted by changing the temperature of the hot air from this heat gun. For example, in our device, if hot air set it as 250 degrees Celsius, the temperature of the inside of jar was 120 degrees Celsius. That temperature reproducibility for reaction is very high. Please see details in our paper. So the effect of the heating was very powerful. The reaction was complete only 5 minutes at 120 degrees Celsius. The reaction is much higher, faster than solution process that requires 24 hours to complete. But the reaction was lower than mechanochemical reactions. So we then applied this method to other insoluble materials. This is a chart that shows the solubility difference of the aromatic halides. We first check the reactivity of the compounds whose solubility is similar to carbon 60. We call these compounds class 1 compounds, like this. So class 1 compounds also react in solution, but requires long reaction time, like 24 hours. But a high temperature ball mill gave the products only for 5 minutes with generally higher yields than solution conditions. These are another examples. These compounds would be variable as organic materials. Such compounds also can be synthesized through the some mechanochemical reaction conditions, much shorter reaction time compared to the some in solution conditions. The next, we check some more insoluble materials whose solubility is less than 1/10 that of the fluorine, and is comparable to that of the solubility is just comparable to the phthalocyanine, like this. We call such compounds class 2 compound. These class 2 compounds can also react in solution, but the yield was very low, like as shown here. For example, the yield of the cross-coupling reaction in solution was just 24% after 24-hour reaction time. But in the mechanochemical reactions, the reaction time only requires 1.5 hours, and the yield was much higher than solution reactions. So this is another examples. The yield of the ball mill were higher than the some yield obtained from in the some solution reactions. The reaction time is much shorter compared to the some solution reactions. So this is another examples. The yield of the ball mill were much higher than the solution result of the solution reactions. And this such type of compounds would be very useful for the material science. So finally, we try to use the ball mill conditions for much insoluble compounds that cannot react by any other methods. The solubility was less than 2 or 3 order of the magnitude compared to the some fluorines. So these compounds are very insoluble and cannot react in solution reaction. No product was obtained in solution reaction conditions, but under the ball mill conditions, we found some cross-coupling products in moderate yield. So this compound is a pigment and practically insoluble to any solvents, but however, we got the product in moderate yield under the mechanochemical reaction conditions. We also try to synthesize a new luminescent materials from this pigment. This cross-coupling products gave a very bright fluorescence under the UV light illuminations, and with new structure motifs showing the powerfulness of this approach for finding new variable materials from some pigment compounds. So we believe that the solid-state ball mill cross-coupling reaction can open the new field of the organic synthesis of insoluble materials, where we could not access by solution phase reactions. So next, I would like to talk about the synthesis of mechanochemical Grignard reagents. As you all know, Grignard reagent is a classical carbon nucleophile discovered by Victor Grignard in 1900. And since his discovery, it has been widely used all over the world. However, this reagent was considered to be unstable to air and water, and it needs to be synthesized in solution. So, the synthesis of mechanochemical Grignard reagents had been attempted by many pioneers with partial success. However, their versatility as carbon nucleophiles at the same level as Grignard reagents synthesized in solution had not been confirmed. There was room for improvement, in my opinion. Therefore, the synthetic conditions for the mechanochemical Grignard reagents were very thoroughly investigated in our group. As a result, it was found that the Grignard reagents could be synthesized even under the mechanochemical conditions by adding the approximately 3 equivalents of THF. This reagent reacts with a variety of electrophiles in the same way as the Grignard reagent synthesized in solution. Also, for short period of time, we can open some jar and we can add the electrophiles after the generation of the some Grignard reagents without any significant loss of the yield. This mechanochemically synthesized Grignard reagent reacts with a variety of carbonyl compounds to give some corresponding alcohols. But this is a very tough work because Grignard reagents has a very long history. Of course, some tremendous results of some research already reported. So we should check the lot of compounds to show some mechanochemical Grignard reagent shows a similar reactivity to the conventional Grignard reagents synthesized in the solutions. But my great colleagues did this very tough work. It takes about 2 years, but they finally complete this very long research project. This reagent can be used also for the Kumada-Tamao cross-coupling reaction in the presence of nickel catalyst. Some Kumada-Tamao cross-coupling reaction is a very classical reaction between alkyl halide and some aromatic Grignard reagents. But of course, such a cross-coupling reaction was studied in the solution reaction conditions. And of course, this is the first example of some mechanochemical Kumada-Tamao cross-coupling reaction. So one of the features of the mechanochemical Grignard reagent is that it can synthesize Grignard reagents from insoluble halides, which is difficult to synthesize using a usual solution-based Grignard reagent synthetic method. The reaction for this halide, this has a very low solubility in organic solvent. The reaction, Grignard reaction from this organic halides not proceeded at all in solutions. No product was observed after the reaction with aldehyde. However, under some mechanochemical reaction conditions, we found some moderate yield of some addition products of the Grignard reagents and aldehyde. So we also tested the other organic halide. This has also very low solubility in organic solvent. This also shows a very low reactivity against magnesium metals, but in the solution, but mechanochemical reaction condition, we found some moderate yield of the addition product after some Grignard generation of the aldehyde reactions. We also try to improve the yield of the Grignard reagents right now. So we are now very good method for some improve this reaction yield. The reaction yield is now reaching the about 90% already. We will publish the results of the such improved method very soon. So we also perform the NEGZAFS measurements with our collaborators, Professor Hikaru Takaya, Kyoto University, to confirm whether Grignard reagents were indeed produced under the mechanochemical reaction conditions. The spectra of Grignard reagents obtained by mechanochemical synthetic method were consistent with that of a Grignard reagent made in some solution systems. We are now studying the structure in more detail because some NEGZAFS method can give us more information about more detailed structure of Grignard reagents, how much aggregations in some mechanochemical reaction conditions, or how many THF actually coordinate to the magnesium centers. So by combining the DFT calculation of the Grignard reagents, so we believe that we will find the more detailed some complex structure of the Grignard reagents generated by mechanochemical reaction conditions. Shortly before our publication, Carstenborn group reported the generation of the mechanochemical Grignard reagents and its reaction with carbon dioxide. They published this paper in August 27, 2021 in the Chem Archive. And after that, they they published formally this paper in Angewandte. So they use lithium hydroxide for activator of Grignard reagents. So next, I would like to talk about some Mechano-Redox reaction using the piezoelectric materials. Piezoelectric materials are very interesting compounds that generate an electronic current when mechanical pressure is applied to the materials. Piezoelectric materials are very often used in everyday life, such as some mics or speakers, such as stoves. So for example, in such a burner, when a mechanical stimulus is given, sparks generated and the gas can be ignited. Since such piezoelectric materials are very cheap and have a low toxicity, I thought that it would be very interesting if an electrochemical reaction could be carried out using such a piezoelectric materials in combination with some mechanochemical reaction conditions. When considering this reaction, I refer to the photoredox reaction. In the photoredox reaction, electrons move from the photoexcited catalyst to the organic compounds, and the generated radical species produce the desired product. So this is a research topic that has been very actively studied in recent years, but it is thought that it cannot be applied to the large-scale reaction or some colored compounds that can absorb some light. So we thought that the similar redox reaction would be possible if a similar electron transfer originates from the mechanically stimulated piezoelectronic compounds under some mechanochemical ball milling reaction conditions. So based on this idea, my colleague, Dr. Kubota, who is a very wonderful scientist, thought that the following reactions. We use such a diazonium salt as a reaction substrate. The radical generated by the electron transfer from the mechanically stimulated piezoelectric materials can generate the phenyl radicals And such phenyl radical can react with aromatic compounds or divalent compounds to produce some cross-coupling product or Boreng product. So when these compounds were mechanically stirred and reacted with ball mill, 40% of desired coupling product was first obtained. So increasing some frequency of ball mills improves the yield, and the reaction did not proceed without barium titanate. That is some key compounds for piezoelectric reactions. So furthermore, if barium titanate was not mechanically stimulated, or if the reaction is attempted in the solution, the reaction did not proceed. However, when other ceramics with piezoelectricity was used, some zinc oxide or lithium niobate, the desired product was obtained with reduced yield. We concluded that the mechanical agitation and piezo materials were necessary for this reaction. We concluded this is consistent with a Mechano-Redox reaction that we initially thought to occur. So we have applied this mechanical redox reaction to the many substrates for cross-coupling or borylation reactions. So we next try to use this some piezoelectric materials hammering reaction conditions. So we just mixing the substrate and the piezoelectric materials in the plastic bags, and we use a hammer to agitate some piezoelectric materials. So like this. And we finally found that borylation also occurred in such a little bit strange reaction conditions. I think this is world's first borylation by hammering. So after the hammering 200 times in air, we found some moderate yield of the products. These are very funny reaction conditions. So just after our some research report, Professor Kassenbaum groups also and Dr. Hernandez reported some reaction with similar concept. They reduce some kappa 2 catalyst to kappa 1 by using the barium titanate and mechanical agitation to promote this cyclization reactions. So we also reported other different types of mechano-redox reactions for trifluoromethylation reactions by using the barium titanate compound. So this trifluoromethylation reaction is very important for pharmaceutical pharmaceutical production. And I believe that in near future, we can develop the more some various types of mechano-redox reactions. So this is a summary of some research results we published from 2018 to 2022. So fortunately, we found many different type of cross-coupling reactions and mechano-redox reaction. And we also try to use mechanochemical reaction to the polymer functionalizations. So I strongly, after some several years, some research, I become to strongly believe mechanochemical reaction can be a very key technology to revolutionize organic synthesis or organic chemistry to more convenient or more useful or more some environmental friendly in future. So maybe I have many ideas to for the mechanochemical reactions other than these results. For I'm very excited to do this field by field about the mechanochemical synthesis. So finally, I would like to express my sincere gratitude to all the collaborators for their great cooperation in the progress of this research. And I also sincerely thank them for their cooperation such such maybe I also appreciate for the grants to support our research. Okay, thank you very much for kind attention for my presentation. Thank you. I'm very happy to have a question.
Thank you very much. We have a few questions from the live audience.
Okay.
First, ball milling has superpowers.
Mm-hmm.
Very interesting. How do you limit or eliminate impurities from jars and balls during milling?
Okay, such eliminate some effect of the elimination, you mean, maybe? No, or just maybe?
It just says limit or eliminate impurities.
Impurities, eliminations. Okay, some maybe, is that the question for the purification of the product?
I think so, give it a shot.
Okay, for the purification is a very different problem, different issues. So maybe at this stage, purification, we use a very standard technique for silica gel chromatography. So maybe if you want to eliminate, if you want to remove the impurity from the jar, you just do some standard technique for the silica gel chromatography. So maybe purification separation is another problem. If we try to we don't use any solvent. We should develop the new method for separation, purification of organic compounds of the products.
All right, thank you. Next question. In the mechanochemical redox reactions, you showed reactivity for various piezoelectric materials.
Okay.
Did the yields scale with redox potential?
Yields?
Did the yields scale with redox potential?
Yield scale. That's a very big problem because maybe some redox potential for piezoelectric materials is in some powder is very difficult to measure. So we just know maybe concrete some results for some redox potential for piezoelectric material in the powder. That's a very big problem. So we first expected that some redox maybe power is very high because you see such piezoelectric material can make a electronic spark. So I hoped such a piezoelectric material is very powerful for the redox reaction, but for after the experiment, some maybe not so very strong. So maybe kind of loss of the energy or some electron transfer is a very big problem. We should have a more breakthrough to improve some efficiency of some redox reaction by using the mechanochemical reaction conditions.
All right, thank you. Next question. Have you tried other ferroelectric or piezoelectric materials for your quote with a hammer synthesis? And
okay.
Do you think, here's the follow-up is, do you think all piezos will act the same or offer unique properties?
I'm sure not all piezoelectric shows a similar effect, but we tested so many piezoelectric materials already because but the barium titanate is best so far. So, but I think the much more higher, much more some powerful piezoelectric material we should find in future. Maybe more than 20 different piezoelectric materials already tested. But such tested example was less powerful compared to barium titanate.
Thank you. Here's a related question. You showed barium titanate was required for the reaction. What makes barium titanate special or better than other materials?
I don't know. Maybe for example, maybe there are many other some piezoelectric materials. For example, PZT is known to have a much higher piezoelectricity, but PZT have no reactivity for our purpose.
All right, I think we have time for maybe one more. Next question. What is the reason behind selectivity of solid state reaction with dibromo-aryl derivatives?
Okay, that's just came from the reactivity difference of liquid and solid. Sorry for my explanation is not so very nice. Maybe dibromo compounds is liquid materials, and that react very quickly. But some mono cross-coupling product is solid materials. That solid material is not so very reactive compared to some liquid dibrom compounds. Such a reactivity difference is key for the selective cross-coupling reaction.
All right, excellent. Well, thank you again, Professor Ito, for your excellent presentation.
Thank you.
We appreciate it.
Thank you very much.
Thank you, Professor Ito, for that outstanding presentation. Some mechanochemistry discussions. If you missed any of the presentations before in the seminar series, they are on YouTube, and I encourage you to check them out. Also, we have an excellent slate of speakers lined up for this upcoming months, and we encourage and hope that you will join us here at Mechanochemistry's discussions for all of them. Thank you again.